From the Oregon State University Extension Service, this is Pollination, a podcast that tells the stories of researchers, land managers, and concerned citizens making bold strides to improve the health of pollinators. I'm your host, Dr. Adoni Melathopoulos, Assistant Professor in Pollinator Health in the Department of Horticulture. If you're like me, when you're walking within a region, let's say in the Willamette Valley, if you go to a nature preserve or an agricultural setting or an urban environment, all three of these exist in the Willamette Valley, you may notice some of the same pollinating insects, but there's a subtle difference between the composition of the pollinating insects in each one of those areas. I've always been interested in this topic of why that is, what's driving those mechanisms. So I was really excited last month at the Entomological Society of America meeting in Denver to hear Dr. Kayla Perry deliver a talk on just this subject. She's a postdoctoral fellow in the Department of Entomology at Ohio State University, and her research is looking to disentangle local and landscape level drivers of the kind of insect diversity that we see across landscapes. But before we get started, two quick announcements. The annual Orchard Bee Association is having its annual meeting this year for the first time in Corvallis, Oregon, at Oregon State University. It's going to be a hybrid meeting, so you can come in person or join online. I'm going to put the link to the registration in the show notes. There's going to be some great talks by both people who've been, practically managing mason bees, but also past guests, for example, like Kate LaCroix and Teresa Pittsinger, so don't miss out. And also over the next 2 months, we're going to be fundraising for the Oregon Bee Atlas. We really need some donations to help us identify bees using molecular techniques, but also to pay for our taxonomist, Lincoln Best. If you want to donate, it's a tax-free deduction. It's a 501c3. So again, I'll put that in the show notes. And without further ado, let's go to Understanding Community Bumblebee Assembly with Dr. Kayla Perry from Ohio State University. Okay, welcome Dr. Perry to Pollination.
Thank you. I'm so excited to be here.
Well, here is Denver. We're at the Entomological Society of America, or this huge conference center. It's been really great sort of seeing all these wonderful talks about pollinators.
Absolutely. Happy to be here. Happy to be out of my house to see other people.
It has been really wonderful. And it was really great because I got to see your talk. I didn't know about your work before. And that's one of the wonders of going to a conference like this. You get exposed to so much work that you just didn't know was going on.
Absolutely.
And the thing I was really struck by in your research, it was, this issue of, everybody is really interested in planting for pollinators in their gardens. And I always get asked this question all the time. It's like, how do I know if I'm having an impact? Like, how would you even measure that? And what I really appreciated in your talk was, how would we measure this? How would we be able to assess, the success of something like a habitat augmentation in an urban area, or how pollinators work in an urban area. So can you just broadly set up, you had these concepts, I'm doing a lot of talking, but you talked about 3 levels. People often say, I have a diverse amount of bees in my garden. Mm-hmm. And you set up 3 levels of diversity. Can you explain those to me? They seem fascinating, seem to really explain a lot in terms of what we see on the ground.
Yeah, absolutely. So I'm really interested broadly in understanding how disturbances structure insect communities, both what species we find in a habitat patch, but also their function. And so I have taken an approach to answering some of these questions by looking at community assembly. And essentially, this is just understanding what species we find at a particular habitat patch and why.
Let me get this right. Community assembly is like, I can just imagine the kids at the assembly at the school. It's when all the biodiversity sort of assembles in a local spot.
Absolutely. Yeah, so there is some given number of species that you might find within your region, but if you go out to your backyard, you only find maybe a subset of those species at your house. Uh-huh. And so I want to know, why is it just those species that are in your backyard compared to other species that you might find at a forest patch, down the road, or at your neighbor's house, or some other green space type.
I remember when you were, so I get this. So you've got this, there's got to be, the work that you were presenting was on bumblebees. So you can imagine in a region, people found all these bumblebee species. And then at these local levels of your garden, you're seeing only a subset. Invariably, you're only going to see a subset. But the thing that I remember in the intermediary is that you have these kind of big chunks of land use, like agriculture and urban spaces. And those may admit certain pupils into the assembly.
Absolutely, yeah. So what I talked about yesterday and what I'm really interested in is how humans might influence what species we're finding at a particular habitat patch. Mm-hmm. And so, do we see different species when the green space is surrounded by primarily agricultural land compared to a green space surrounded by primarily urban land? Mm-hmm. And how maybe the amount of natural habitat surrounding that site might influence those patterns.
It brings me back to what you were saying earlier as well. I can imagine in terms of disturbance, a city probably is a large, growing area of disturbance, mm-hmm. and that invariably the disturbance itself and the surrounding area as well, but that must be kind of a dynamic between the disturbance and what species are found there from the periphery.
Absolutely. Previous research has found that urban disturbance typically selects for more generalist species. You also tend to find more non-native species in cities. And so some of my research has tried to go beyond just looking at species, but also looking at what traits. And so, you can see what species are in the city or in, an ag field, for example. But if you want to apply those results to, say, another state or another country, it's really hard to do that when you are just looking at a list of species, right? You might not find the species that I find in Cleveland or Wisconsin, in Germany, for example, mm-hmm. or Europe. And so if we take a look at functional traits, which is essentially different morphological, physiological, behavioral traits of the species, then those results are more broadly applicable, and you can say something about their function that those insects are providing.
Give me an example of that. What do you mean by functional trait? Like what's
a great one is body size. So insect ecologists often use body size or wing development. So body size relates to a lot of metabolic processes. It can also relate to reproduction within insects. And wing development can relate to dispersal capacity.
Oh, yeah. So for example, clearly you have a bee, you might have a bee that has a larger, bigger body size. It might disperse further. And so it sort of has like a dispersal trait about it.
Bees tend to be considered more mobile. So some of my work with beetles, I can actually sort of distinguish those two because some are flightless and some are not. So depending upon what group you're looking at, that dispersal capacity trait can be more or less extreme.
Okay, so that's great. So there's another example right there in terms of beetles. Do you have wings or not? Functional trait. Okay, all right.
Yeah, and some of my previous work has found that cities really select species that are good dispersers. We don't see flightless species in the city very much.
Oh, yeah.
And so, major landscape change, such as urbanization, can influence the species that you find there just based on dispersal capacity.
Okay, this is great. I think this sets everything well. I think I've got the groundwork to sort of learn more about your research. So you were interested in this question of you have these regional pools of bumblebees, and you've got different land uses in Wisconsin where your study is taking place, and you wanted to sort of figure out how these traits relate, how the traits might, I suppose, filter or something?
Filter, yeah.
To what you see on the ground. Tell us a little bit about the broad design of the experiment.
Yeah, so this project is in collaboration with Ohio State University, which is where I was when I was conducting it, but also University of Wisconsin. And so our partners at the University of Wisconsin set up a design along an urban-rural gradient. So they were sampling bumblebees in green spaces in sites that were primarily dominated by urban land cover or ag land cover. Okay. And so this allowed me to test the hypothesis of whether different land cover types result in different filtering of traits. And so you can think of a filter as like a sieve, is sort of how the analogy goes, where species that are able to survive in that habitat sort of pass through that filter and exist, whereas other species that can't are sort of left out. They can't pass through the filter.
They might by happen chance land in the city, but their traits are just not well adapted and they never make it.
Absolutely. Or they can't even get into the city.
Gotcha.
So it can happen at multiple scales. They either can't get in there, or once they get there, it's not right and they can't survive and reproduce.
Okay, all right. So you've got this gradient, urban-rural gradient, and then tell us the next step. Well, I guess people you need observations of bees.
Absolutely, and I was not involved in that aspect of the study. So the Wisconsin team went out and they did their sampling along transects, and they provided me with a data set of the species that they found.
Okay, so you have a data set where you have bees at sites along this gradient. Imagine a site's a little mile or so in diameter.
They did transects, so they walked through a green space and netted bees.
Okay, so you've got all these sites. You've got the community assembly at this one site looks like this, and another one looks like that. How were you able to sort of understand how the filter was operating from these observations?
That's a great question. And so I looked at species and I also looked at traits. And so in order to do that, I had to go into the literature and figure out what traits these different species had. And so a couple that I looked at were body size, and I actually measured those on specimens. And so I looked at some number of specimens and I measured body size. I also measured the wing length to look at their dispersal capacity. And I also looked at some traits related to the corbicular, the pollen basket. We looked at how long that pollen basket was and also how hairy it is, so how long the CD were coming off of the pollen basket.
Oh, right, because if you look at a corbicula, this is the pollen-carrying basket on a bumblebee's leg, and honeybees, I guess, are the other group that people will see these on. It's nice and broad, but then it can be fringed with hairs, and some of those hairs can be quite long.
Some of them can be quite long, yeah. There's quite a bit of variation, actually, between species on how long those hairs are.
Oh, I also remember this. If for people who are geeky and have gone through the Williams bumblebee key, the shape of the corbicula is one of the characters you use to determine, some of them got this narrow. Anyways, there's a lot of variation between the species.
Yeah, and it's a trait that actually hasn't been used in bumblebee functional work. So that's something that I wanted to bring to this project. I also measured the hair on the thorax to see how hairy the bees were. There was also a lot of variation in that as well. It was a bit challenging to do, but that's also a new trait.
Well, I can imagine, because some species have the characteristic bald spot.
Right, and sometimes, depending upon the specimen that you have, the hair's all smushed over, or you have the greasy lipids on them, and so it was a bit tricky, but it was fun.
Okay, so you've got these bees. You've got them sort of. Not only are they just species A, B, C, but now you can sort of think of them as kind of carriers of traits, I suppose. Yeah. So another trait we looked at was tongue length. And so you might have, where we have, 9 species that were collected, then we can group them based on, do they have short tongues? Do they have long tongues? And then what does that say about the resources that they're using and what flowers are they pollinating? Well, that would make sense. I mean, I imagine anybody knows something like a deep current flower, only very long tongue bumblebees get in, the short ones can't make it. Okay, that sounds great.
Yeah. And so then once I have these trait data, then I can look at how these traits differ among our different sites. And one of the ways that I wanted to look at community assembly is to see whether the species and the traits that we have are unique. And particularly whether they're unique compared to the species that we might find in the region. And so I went back to the literature and I identified all the species that the team could have collected. So, and I'm calling that the regional pool.
So this is just going through historic records or contemporary records, and you just, people saw this, and so you've got this is the limit of species that you're likely to find in this whole area.
Surrounding Madison, Wisconsin, in particular.
Right. Very cool.
Yeah, and I used Bumblebee Watch, which is a citizen science initiative, and I determined a conservative estimate of 16 species.
That's
that
amazing.
The team, it's actually quite a lot.
Yeah.
But then the team only collected 9. And so I wanted to know whether there was something unique about those 9 species compared to the 16 that they could have collected.
Aha, yeah.
And so to do that, I used a null model technique.
A what?
A null model technique, yeah. So I basically generated a bunch of random communities. So given our 16 species that we could have found, we've got our observed 9 species that we did collect. Well, let's just I created 999 random communities.
You didn't want to do 1,000. That was just
no, because 1,000, our observed scores is 1. So the whole data set together is 1,000.
Oh, okay. I see the symmetry here.
Yeah.
So you kind of simulate this. You say, well, if we just rolled the dice with these 16 species,
exactly,
I should see some here. Okay, I gotcha.
Yeah, and so I essentially randomize our species matrix, and I also randomize the trait matrix.
Okay. Oh, okay.
So I randomize both of those with some constraints, of course. And so, if, for example, if 3 species were collected at a particular site, each random null model iteration is only going to pick 3 species randomly to put at that site. So there are constraints. This isn't the complete Wild West here. But then we can look at all of those random communities and say whether the bees that we actually collected are unique in some way.
Okay.
So that's the null component.
So we've got these observed bee assemblies, and then you have one that, if it was just random, it had nothing to do with these traits, had nothing to do with it should look like this. And so I guess you have something to compare to now. Right.
And because we do it 999 times, you get a pretty good idea of like what random would be.
Okay.
Essentially.
All right.
And then I can compare the bees we actually collected to these null model communities and say things like, okay, well, are the bees in urban and ag-dominated landscapes larger or smaller than we might expect by chance? Or do they have longer or shorter tongues than we might expect by chance?
Okay, gotcha.
Yeah.
All right.
And so that allows us to put some perspective on what we're actually finding. Like, is it unique or not?
All right. And so, drum roll, please. What did you find?
Well, we found that bees tend to be smaller. This is actually a really important point here.
Okay.
So we're finding that species in ag landscapes and in urban landscapes tend to be smaller species.
Smaller species. Okay, gotcha.
Yeah. And they also tend to be less hairy, which is very interesting, and they tend to have smaller wings.
So in the whole pool, the smaller species that are less hairy and with smaller wings are the ones that are finding disproportionately above a random expectation in agriculture and in urban settings.
They're more prevalent than we would expect based on chance.
Wow, okay.
We're also seeing that species that nest above ground, so like in trees or in grass clumps, things like that, those are also more prevalent than we would expect. And our kleptoparasitic species that require the host bumblebee species to survive and reproduce, those are less prevalent than we would expect by chance.
Okay, so I guess the nesting above ground and below ground is a functional trait. And for listeners who don't know, some bumblebee species love to nest above ground. Some only nest below ground, and there's some that kind of switch back and forth. And so we are seeing more of the ones that nest above ground in both urban and agricultural landscapes. And we have these kleptoparasitic bumblebees that don't make their own nests. They kind of go in and they assume another nest. They also seem to be dropping out from what we would expect by random. Okay. Although this is very interesting. So there seems to be some kind of like preference in these landscapes for certain species.
Absolutely. And you mentioned below ground nesting species, and we actually found that those were present as we would expect by chance. So they overlapped with our null model results. And so we didn't see that those species were more or less prevalent. It was just, this is what we would expect.
Okay. The last thing, I remember this in the talk, which I was we spent all this time talking about corbicula, but there seemed to be a signal associated with this trait.
Absolutely. Let me pull this up because I forget.
Oh, yeah. Listeners, we are
So you can see
looking at a laptop here on a.
Yeah.
Okay, here we go.
So this figure includes most of the traits that I measured directly on specimens, which is a lot of fun. It's also very time-intensive microscope work. But see, as I mentioned, we're seeing bees that have shorter wings. We're also seeing bees that have wider heads and larger eyes.
Oh, larger eyes. Okay. Oh, yeah, I guess some of them have...
So it's length in particular. Right. Larger eyes. We see bees that are less hairy. And we are seeing bees that have longer setae longer hairs on the corbicula.
So shorter hair on the body.
Yep. Longer hair on the corbicula.
Straight, nature. Let's be consistent here. Okay. All right.
Yeah. And so, wing length would relate to dispersal capacity. And, we're seeing some resource capture traits show up here in terms of thorax hair length and also the hair on the corbicula. And so if you think about what species are being over underrepresented and what traits are being over and underrepresented, nesting traits, above ground nesters, smaller species, and these traits related to dispersal capacity and resource capture are important.
I suppose it begs the question why, and I know, I remember my colleague at OSU has worked on urban landscapes and looking at solitary bee species, and there seems to be some environments where you get a lot of cavity nesters as opposed to ground nesters. I can see a pattern emerging here, but what do we make of some of these trends? And I guess one has to be careful because the traits are functional, but how they're being used in that specific environment. Especially, I'm looking at these. The trends seem quite similar for urban and agriculture,
yes,
but they're very kind of different places.
Yeah, and there is a lot of variability among the sites, and so that's also important to note that, not every site is the same in its composition, and also in the landscape that's surrounding it or the local plant community. And so we do see variation, particularly with the agricultural sites. In some of the other figures, the urban sites are very tight.
Well, let's take a quick break. I want to come back because I see all of these dots, and I think I'm very curious about the variation that occurs within an agricultural or an urban landscape. So let's take a quick break and let's come back and explore that because you've looked at this too.
I have, yes.
Okay, and we're back. All right, so you also looked at you have a lot of variation within in what you would call the urban landscape. So sure. one backyard is not like another backyard, or one region. I imagine a place that's got a big park or has a forest next to it. It's not the same as something that's like in downtown Denver where we are today. So tell me a little bit about what you find in that kind of setting when you're looking at the broad spectrum of sites kind of nested within these locations.
Absolutely. As we mentioned before the break, I noticed a lot of variation among my sites, both in the urban dominated landscapes and in the agricultural dominated landscapes. And I really wanted to understand, okay, what might be contributing to this variation? And so I immediately thought, what about the amount of natural habitat in these landscapes that are highly urbanized or with agricultural intensification? And so around Madison, Wisconsin, that tends to be forest as well as wetlands. And so I wanted to calculate some different landscape metrics to try and tease apart some of this variation and see how the amount of natural habitat surrounding those green space patches might be influencing the traits that we find there. And I found some really interesting results. So if we just look at percentage agriculture in the landscape or percentage urban land cover and sort of really look at the gradient, we see that long-tongued bees tend to be more prevalent in agricultural landscapes, and short-tongued bees, tend to be more prevalent in urban landscapes.
So if you got a site and it has a disproportionate amount of agricultural land around it, it seems that the species that have long tongues are they're higher than they would be by chance.
Yeah. Absolutely.
Okay. All right.
Yeah, and if we look at what species those are, the team collected Bombus oricomis and Bombus fervidus. So those species have long tongues. Yep. And if we look at short-tongued species, this includes Bombus griseocolus, Bombus rufosinctus, as well as the federally endangered Bombus affinis, which they did collect some.
Well, I've heard this. I follow. I have colleagues at the University of Minnesota, and oftentimes the bumblebee atlas that they have there, they've been spotting it in Minneapolis. It's kind of okay, all right. Yeah. But this might be because the filter of Minneapolis is welcoming to Bombus affinis.
Perhaps, okay. Yeah. And there could be other, in addition to landscape, floral resources and things that I didn't necessarily look at least not yet.
Well, I imagine the other thing is you may have flowers that a bee likes, but there's another bee there that's just way more competitive for it, and it gets bumped out, and so I imagine it gets complicated. So maybe the bee community that's there.
Absolutely. Different competitors at a particular habitat could influence whether a less common species can successfully survive and establish. Okay. And we do see that some species are very common across all of these sites, including Bombus impatiens and Bombus bimaculatus and Bombus griseocolus. Those tend to be really abundant along this urban-rural gradient.
Okay, so let's dig in deeper to more fine scale these. What other kind of functional traits do we see associated with what we might see in?
Yeah, I took a look at the amount of natural habitat. So as I mentioned, primarily forest and wetlands. I looked at how connected forest habitat patches were, as well as how large the largest forest patches, so one contiguous forest patch in the landscape, sort of how large that was. And we saw some interesting patterns with traits. I mentioned before that the species we're finding in these modified landscapes were primarily smaller species. And of those species, the larger ones are actually present in sites that have more natural habitat surrounding them.
Okay, let me get that. Let's just walk to So in general, by chance, compared to by chance, you get smaller bees. We established that in the first part of the episode. But the larger species on that spectrum are more predominant when you start to have more natural area.
Absolutely.
Oh, that's interesting. So it does suggest kind of a mechanism, perhaps. It's like natural areas seem to favor bees that have a larger size.
Yeah, and that could have potential conservation implications because, as I mentioned, right, we're losing larger species, but we see that larger species need natural habitat. And so that could be a potential conservation avenue to focus on.
Oh, fantastic. But anything else that popped out of this analysis? Listeners, I'm looking at this graph, and it is a work of art, but there's a lot of arrows here.
So in addition to larger species, we also see hairier species. So they have longer hairs on their thorax, which could influence pollen collection, for example.
Well, it's the same trend that we saw on the sort of the broader scale.
Yeah.
I'll be darned.
Yeah, and sort of opposite of this, with increasing forest patch isolation. So this would be an opposite measure of connectivity, right? So with increasing natural habitat, we tend to see increasing connectivity. Opposite of that, we see increasing isolation.
Oh, yeah.
And so as we see increasing forest isolation, we see medium-tongued species, which tend to be the very common species like Bombus impatiens. We also see species that have wider heads, so that can affect the resources that they use, and longer eyes, which was really driven by Bombus vagans. Bombus vagans has very big eyes compared to the other species.
Oh, okay. All right.
And there's this one other functional trait that I haven't really mentioned before, and it's worker body length variance. And I find this to be really interesting. And so essentially, it's a measure of how variable a species' body size is.
Oh, I never thought about that.
And so if you open up like bees of North America, for example, like a field guide, and you look at each species, it'll give you a range of size for that species. And so if you just take the difference between those two numbers, you get a measure of its variance.
Because I intuitively, I think there's some species in Oregon that can have like a much wider range of size. I think of like yellow-headed bumblebee, Bombus vozesensky. The first workers are just tiny, and you really do have a range. Like those tiny ones are disproportionately small for that size of bee. Okay, all right.
Yeah, and so we see species that have greater variability in their size, this plasticity, tend to do better or are more prevalent in urban sites. And also this is falling in between our forest patch isolation. And so in sites that have more isolated green space patches, in this case forest, or in highly urbanized sites, we see species that have this plasticity in their body size being more prevalent, potentially as a adaptive.
Well, this is fantastic. I can see how, if I was an urban planner kind of looking at this work and how it pencils out, there is a way in which having a variety of landscape types around a city, there'll be something for everyone. And knowing that you're not going to be able to maybe, not all species will find a home in the city. I imagine that becomes really important in terms of trying to keep bee diversity up in urban as well as in agricultural areas.
Absolutely. And so the next step with this work is I'm hoping to take a look at some of these landscape variables, natural habitat, forest connectivity, and use some of the null model data that I generated to perhaps identify some thresholds so I can make some recommendations about what we might want to do at a landscape scale to help support bumblebees.
Well, fantastic. Well, this is really great. I know you've got to rush off to another meeting, but maybe we have just a quick moment. We're going to do our answer our guests these 3 questions. I'm so curious what yours are. We'll be back in just a second. And we're back. Okay, so 3 things real quick. Do you have a book recommendation for our listeners?
Oh, gosh, this is the one that's been stumping me. I guess. So with my functional trait work, I've primarily studied beetles. So bumblebees are a whole new research avenue for me. And I've been very interested in learning about bumblebees, but my background is actually in beetles.
Okay.
And so there's this one beetle book that is like my beetle Bible.
Ooh.
And it's essentially a natural history book of ground beetles.
Really?
And it's been a wonderful resource for pulling functional trait information. So it would be great if someone could create a book like this for bees.
So this beetle book is for North America?
It is, yeah. North America above Mexico. And it's ground beetle natural history.
Oh.
So I think we need a parallel for bumblebees or for bees in general. And this is my challenge to listeners.
All right, listeners. The gauntlet has been laid down.
Yeah, I could have really used that when I was trying to find these traits.
I mean, it's, I guess the thing is like with a lot of, I remember you were talking kind of going to Discover Life. There's various places where there's some of this information squirreled away, but it's not compiled very well.
Correct.
And in some cases, it's just not known. And it would just be nice to know that. I'd love to have a resource like that.
And to have it all in one place.
Oh.
It would be a really big task, but somebody out there should really do it.
Somebody young, because you're going to need decades to do this. Okay. So the next question I have is your go-to tool for the...
Yes.
Yeah, tell us.
I am a huge fan of dichotomous keys, and it doesn't matter what taxa I'm looking at. It's an essential resource for all the research that I do. I'm not a proponent of people using Bug Guide and other
those
sort of online
keys.
Yeah, I'm all about the paper dichotomous keys, and I collect them.
There's lots of them. There's tons when it comes to bees, but there's something great about having the paper copy there, especially when the illustrations are, there's good illustrations, and you can really see these traits, and then the payoff is that suddenly this world of bee biodiversity opens up to you because you can tell the difference between that and that.
And you're learning about the morphology as well, right?
Yeah.
And then, it's just a great skill to be able to use one of those because they are challenging. Like if you're going to pick up a dichotomous key, you have to know all that morphology. So there is a learning curve.
There is.
When you want to use them. But it's a skill that you can then apply to any group that you want to learn.
And I think people get scared of it, but it's one of those things you put 10, 20 bees through a key and you actually have reference material there. Mm-hmm. You spot it and you see real trained taxonomists and they're just kind of glancing at it. Like the key has already been like reprogrammed into their neurons, and they're just like,
Yep. Yeah, it's a great skill.
Fantastic. Okay, the last question before I let you go is, do you have a favorite pollinator species?
That's a tough question. So with my bumblebee work, my favorite one has been Bombus pennsylvanicus.
Oh.
It's beautiful. It's a large, robust bee. I love the shades of yellow and black. Across bumblebee species, that yellow color can change, right? I just love the contrast and the long face of Bombus pennsylvanicus.
We were, because it's been in the news recently, our taxonomists went through, because there's a couple records on the eastern part of our state, and it's unclear whether they're real records. But I haven't seen them in Oregon. Like if they were there, it's really on its edge of its range. So I really look forward to coming out to the east and seeing it one day.
That sounds great.
Well, thanks for taking the time at a busy conference. We really appreciate it, and thanks for walking us through this complicated world of like why bees in one place look different from another.
Thank you so much for having me. This has been a real joy.
Thank you so much for listening. The show is produced by Quinn Sin and Neal, who's a student here at OSU in the New Media Communications program, and the show wouldn't even be possible without the support of the Oregon Legislature, the Foundation for Food and Agricultural Research, and Western SARE. Show notes with links mentioned on each episode are available on the website, which is at pollinationpodcast.oregonstate.edu. I also love hearing from you, and there's several ways to connect with me. The first one is you can visit the website and leave an episode-specific comment. You can suggest a future guest or topic, or ask a question that could be featured in a future episode. But you can do the same things on Twitter, Instagram, or Facebook by visiting the Oregon Bee Project. Thanks so much for listening, and see you next week.